small, medium. So this is your sampling and this is your mixer. Okay. So sampling is the output entity and mixing is the input entity. Okay. So basically, you want to sample current. So your output should be I naught, right? Because you are sampling current and your output is I naught, and you are mixing it in a shunt manner. So shunt mixer is nothing but a current mixer, right? Shunt mixer is nothing but a current mixer, and therefore your input variable is also a current. So now you can find out the gain. Okay, so gain is output signal to the input signal. So output signal is current and input signal is also current. So therefore, this gain can be considered as the current gain AI. So basically, for a current shunt feedback, you're going to have a current amplifier. All right. So let's draw the equivalent circuit of current amplifier. This is IS. Okay. Now you need to have a feedback signal which is proportional to current itself, right? It should be proportional to current signal. So that means to say I naught should be proportional to IF should be proportional to the current signal. So basically this is how we do it. Okay, before drawing, let me show you, okay, the current sampling network so that you can quickly recall as well. Yeah, sampling network. You see, this is how the current sampling is done. Okay, this is your current source, this is your amplifier, and this is your input current II. Okay, and at the input, you see IF is being derived. So this IF is nothing but the feedback current. Okay, so you see properly. Okay, the IF, we have considered the direction for IF in the downward direction. Hence, what we'll do is we will place a current source in this manner. Okay, and this current source stands for IF. And remember where IF is equal to beta times I naught, where beta is the feedback factor and I naught is the output current. All right. So this is your current amplifier. Okay. This is your current amplifier. All right, fine. So once the equivalent circuit is drawn, okay, you can apply the KCL. Let us apply KCL at node K. All right. So fine, apply KCL. Node K. So what do we get? Input current is IS and the outgoing currents are II and IF, right? So source current IS is equal to IF plus II. Okay, that is equal to II, let me write it as it is, plus IF. So in place of IF, what we can write? we can write this expression, beta into I naught. All right. Okay, in bracket, let me write IF is equal to beta into I naught. Okay, if you are not able to follow. All right. Then, in our input current equation, we have this I naught, but we don't want that I naught to be there on the input side, because on the input side, we would want everything to be expressed in terms of the input parameters. Yeah. Before that, I have forgot. Okay. Forgot to mention, the expected input impedance. So RIF is VI divided by IS. Okay. On the other hand, the input resistance of amplifier is Ri is equal to Vi divided by Ii. Okay. All right. So from the output side, let us try to get a relation for I naught. Okay. So I naught, okay, you can apply current division rule, CDR. Applying current division rule, you can find an expression for I naught. So I naught is equal to main current into resistance of the opposite branch divided by sum of the resistances. On the other hand, what happens when R naught is considered as very large in comparison with RL, you would get, I naught very close to the gain times the input current. Okay, so let's say equation 2 and let's say equation 1. So in place of I naught, you can substitute equation 2. So substitute 2 in 1. So what do we get? We get IS is equal to II plus beta into I naught. So what is I naught? AI into II. So let me write AI into II. Okay, and that is equal to II times 1 plus AI into beta. Okay, let's take this as equation 2. Okay, and then let us define RIF. Okay, we know that I have already defined in the beginning. RIF is defined as VI divided by IS. So VI divided by IS, right? In place of IS, you have equation 2, that is II into 1 plus A into beta. Okay, so that is equal to, can anyone tell me what is this ratio? Voltage by current, VI by IA. So VI by II, we have already defined, right? VI by II is nothing but RI. So RIF is equal to, VI by II ratio, which is Ri divided by the denominator factor, 1 plus AI times beta. Okay, so this is your input impedance with feedback. So this reveals that input impedance with feedback is reduced by a factor of 1 divided by 1 plus AI into beta. Okay, so that's the effect of feedback on the input impedance of a current shunt feedback amplifier. All right. Now let us look into R naught F. Okay, how to determine R naught F of a current shunt feedback. Okay. So to determine, R naught F of current shunt feedback, what we can do is, you can first set IS is equal to 0. Okay, that is open circuit source current. Okay, open circuit the source current, and then you remove RL, and in the third step connect a fictitious voltage source V across the open circuit terminals on the output side. All right, it's just a three-step approach. Okay, very easily you can do it. Let's apply step number one. Let us open circuit the source. So IS I'm going to open circuit. Okay, so when I open circuit IS, this is what I am going to get it on the input side. Okay, and across the open circuit terminals, let us connect a fictitious voltage source V. See, this fictitious voltage source V is nothing but the open circuit voltage which is available across these two terminals. Okay, and due to the closed circuit nature on the output side, there will be a small value of current flowing. Okay, since with a straightforward approach you cannot measure that current, hence we are going for this reduction rule. Okay, so this is our V. Okay, plus minus we have taken, and let's take this as the current circulated by the fictitious voltage source V. Okay, so this is the direction of I, and this is the direction of actual current I naught. Okay, so they are in phase opposition. Okay, now let us define the resistance, output resistance with feedback. So let's define it as ROF. So ROF is V by I ratio. Okay, V by I ratio. All right. So on the input side, you can write down the expression. So first let me write on the input side, apply KCL. Okay, so when you apply KCL, what do you get? 0 is equal to IF plus II, or you can write II is equal to negative IF, and that is equal to negative. Okay, what is IF? We have already written. IF is beta times I naught, so it is negative I naught. Okay, but you know that I naught is equal to minus I, right? Because I and I naught, they are flowing in the opposite directions. So that's the reason you can substitute I naught as negative, and therefore you would get II is equal to positive I. So II is beta times I. Okay, so let's take this as equation 1. We will be needing this equation in the output side. Okay, now let us apply KCL at the output side. Okay, so what do we have? So we have actually three currents. Okay, let's say this is our node K. Okay, so at node K, all right, let us apply KCL. So let me take this as IX. IX is the current which is flowing through the resistance R0. So when I apply KCL, what do I get? I get Ix is equal to, okay, because outgoing current is Ix, and the two incoming currents are I and AI times II, right? So I have I plus AI times II, okay? Or current I is equal to Ix minus AI times II, which is equal to, what is Ix? As I said in the beginning, that Ix is the current flow through R0. Okay, so if you observe carefully, across R0, voltage V is present. So having known the voltage, you can find out the current. So Ix is nothing but terminal voltage V divided by R0. So in place of Ix, we can write V by R0. Okay, let me just underline V by R0 minus AI times I. Okay, let's take this as equation 2. Okay, now substitute 1 into, okay, because I have AI. So in place of AI, probably I can substitute equation 1. So what do I get? I get I is equal to V by R0 minus AI into II, which is beta times I. Okay. So what we can do is, you can group the like terms together. So let me bring this negative term onto the left-hand side. So I get I plus AI into beta into I is equal to, V by R0, or take out I common. So 1 plus AI beta is equal to V by R0, or rearrange the equation such that you get the ratio V by I, and we have defined already V by I ratio is R0 F. So V by I ratio is nothing but R0 divided by 1 plus it is not divided, right? Because it gets cross multiplied. I'm so sorry. This gets cross multiplied. So cross multiply R0 times 1 plus AI into beta. Okay, so that's your what do you say, the output resistance with feedback. So therefore R0 F is equal to R0 into 1 plus AI times beta. Okay, so this shows that with negative feedback, output resistance increases. Okay, so everywhere if you see, it basically alters the input and output resistances or impedances. Okay, so that's your current shunt feedback. All right, now finally we can take up the remaining one, which is voltage shunt amplifier. Okay, so the final one is, you can write down voltage shunt feedback amplifier. Okay, all right. So how do you decide which basic amplifier to be used for this voltage shunt feedback amplifier? Okay, so first is small, second letter is medium. All right, so this is your sampler, and this is your mixer. Okay, so what is that you need? You need voltage sampling, right? And sampler is found on the output side, and your output parameter is voltage V0. Okay, fine. Next, which type of mixer you need? You need a shunt mixer, right? And mixer is found on the input side, and shunt mixer stands for current. So your input variable is current. So therefore, gain you can calculate. So gain is equal to output signal to the input signal. Okay. So what do I have against output signal? We have voltage divided by input signal is current. So basically it is V by I ratio. Hence your gain going to be RM. Okay. So gain is RM. That means to say you need to use trans resistance amplifier. You need to use trans resistance amplifier. Okay, so let us construct the circuit diagram. So first let us draw the trans resistance amplifier. Okay, first let us find out RIF. Okay, before that let us define what is RIF. So RIF is equal to input voltage VI divided by source current RS. Okay, so that's your RIF. So let us write down. Let us define RIF as voltage by current. So that is VI divided by source current IS. Okay, and then let us apply KCL node K. So that's IS is equal to IF plus II. Okay, that is equal to II plus IF. Okay, what is IF? IF is beta into V0, where IF is equal to beta into V0. Because on the output side, you have the voltage signal. So your feedback signal should be proportional to the output voltage. Okay, fine. And where V0 can be substituted from the output circuit. Okay, from the output circuit. So on the output side, okay, apply voltage divider rule on output side. So when you apply voltage divider rule on the output side, what you get? You get V0 is equal to source voltage, which is Rm times II into RL divided by R0 plus RL. Okay. Or let's say if your RL is very large in comparison with R0, your output voltage V0 is approximately, equals to Rm times II. Okay. So let's say this is equation 2 and let's say this is equation 1. So substitute 2 in 1. So you would get IS is equal to II plus beta into V0. Okay. So beta, let me write, into V0. V0 is Rm into II. So Rm into II. Okay. Or IS is equal to II times 1 plus Rm into beta. Okay, let's say equation. We have input resistance with feedback as Vi by Is. So we can substitute. That is Vi divided by Is. Is is II times 1 plus Rm into beta. Okay, so we have the ratio Vi by II as Rm. Input voltage into input current is equal to input resistance. So therefore, RIF, that is the input resistance with feedback, is equal to input resistance without feedback divided by 1 plus gain times the feedback factor. Okay, so that is your expression for input resistance with feedback. So what is the takeaway? So it shows that, with feedback, the input resistance reduces by a factor of 1 divided by 1 plus gain times the feedback factor. Okay, so that's your expression for input resistance. Okay, now let us take up the expression for output resistance with feedback. So normal steps you are going to apply. You are going to, set current source to 0 amperes, and then you are going to remove RL. Okay, and then you are going to connect a fictitious voltage source V across open circuit. Okay. And across the open circuit, you will connect the fictitious voltage source, which just represents the open circuit voltage, plus minus, and say this is the direction of current, and let's say this is the direction of actual load current. Okay, so remember, on the output side, we have I is equal to minus I naught. Okay, I is equal to minus I naught. Okay. Next, you can apply KCL at the input side. Okay, when you apply KCL on the input side, you would get incoming current is equal to summation of outgoing current, that is IF plus IA. Okay, or II is equal to minus IF, which is equal to minus beta into V naught. Okay, which is also equal to minus beta into V, as V naught is V in this case. And let us also define R naught F. So R naught F is voltage by current, V by I. Okay, so that is the expression for II. Okay. Let me write, say this is equation 1 and this is equation 2. Okay. Next, let us pay our attention to output side. Apply KVL. Okay. Since I'm considering the voltage V is greater than the left voltage. Okay. So let me apply KCL in the anti-clockwise direction. So it is V minus I into R naught minus RM into I. So it is V minus I into R naught minus RM into VI is equal to 0. Okay. Or V minus I into R naught minus RM, okay, into VI. So VI can be written as II into RI. Okay. II into RI. Okay, say this is equation 3. Then substitute equation 2 in equation 3. No good use, because we don't want RI to be there in the equation. Okay, just a minute, because we want everything in terms of the output. Sorry, this is RM into II. My bad. Just a minute. Yeah, this is RM into II. Correct? No, this was the mistake. V minus I into R naught minus RM into II. Instead of II, I wrote VI there. That was the mistake. Okay, so this is where is it? Yeah, here, RM into IA. Okay, substitute equation 2 in equation 3. Okay, the same thing, repetition. So what do we have? We have V minus I into R naught minus RM into IA. So what is II? II is beta into V. So this becomes minus beta into V. Okay, is equal to 0. Okay, or you can write I is equal to V into 1 plus RM. Okay, see, this and this is a common factor, right? So minus to minus, it becomes plus. And let us take I into R naught on the outside. Okay, it's okay. Let me rewrite it. So I into R naught is equal to V times 1 plus RM into beta. or you can take out the ratio V by I. So when you take out the ratio V by I, you will get R naught divided by 1 plus Rm into beta. Okay, so that let us take it as R naught here. R naught here. So this equation reveals that output resistance is decreased. Output resistance is decreased by a factor of 1 divided by 1 plus Rm into beta. Okay, 1 divided by 1 plus Rm into beta. Okay, so effects of negative feedback. Okay, effect of negative feedback. Okay, so effect of negative feedback in the sense how the negative feedback is affecting the circuit. Okay, so what I will do, okay, I will make a small table. Okay, first let me write the parameter. Okay, and then let me write the effects. Okay, so the first parameter is gain. Okay, gain. So with feedback, what happens to gain? So basically with feedback, gain reduces, right? With feedback, gain reduces. Example, for a voltage series amplifier, gain with feedback, okay, becomes AVF is equal to A divided by 1 plus A into beta. Okay, so basically with feedback, the gain reduces. Okay. Second one, stability. There is no equation which talks about stability. Okay, because again, it is altogether a different, you could say branch itself, because stability analysis is kind of based on mathematics, but qualitative treatment we can give over here. So stability, it improves. Okay, the negative feedback improves the stability, and I have given you a real-time example also of air conditioning system. Okay, so air conditioning system basically talks about the closed loop or a stable system. Okay, so stability gets improved due to negative feedback, and then you have frequency response. Okay, so frequency response again improves, okay, by a factor of, you can always say by a factor of 1 plus A into beta, improves by a factor of 1 plus A into beta. Okay, and fourth point going to be the subset of the third point, bandwidth. Okay, again, bandwidth with feedback. Okay, a qualitative formula. Bandwidth with feedback is equal to bandwidth without feedback into 1 plus A into beta. So basically, bandwidth will also be improving with feedback. Okay, that's the fourth point. Fifth point will be the distortion. Say for example, frequency distortion. Okay, now frequency distortion, reduces. That is because the closed loop feedback, constantly corrects the error. By correcting the error, the frequency can be, frequency distortion can be reduced. Okay, so reduced again by a factor of, 1 plus A into beta. Okay, so everywhere this feedback factor comes into picture. Okay, then sixth point going to be noise and non-linear distortion. Okay, noise and nonlinear distortion. Okay, so once again, due to the presence of negative feedback, the noise and nonlinear distortion is also reduced, because your feedback system constantly checks for the output and it tries to correct the output. That's the reason noise and nonlinear distortion is also reduced. And then you have finally the input and output resistances. Okay, so basically the input and output resistances, okay, is altered. Okay, I cannot say improved, or increased or decreased, because voltage series will have something like increasing effect, and current shunt amplifiers will have some decreasing effect. So in total, we can say that input and output resistances are altered by a factor of 1 plus A into beta, because everywhere you will find, right, RIF is equal to RI into 1 plus A beta, or sometimes you would see RIF is equal to RI divided by 1 plus A into beta, where A is amplifier gain and beta is the feedback network gain. Okay, so these are the major effects of negative feedback. So in exam, for 6 to 8 marks they have asked. So probably you can draw this table and you can just explain. Okay,